Thank you. Thank you for the introduction. Thank you also so much for your invitation, for giving me the opportunity to present. This is an amazing program. I mean, just to have people from different backgrounds to interact, and this is an exciting time. We heard some talks. We're going to hear also some more talks about the interplay of quantum gravity theory and experiment. So my talk is going to be mostly theory, and it's going to be related to also hopefully some of the other talks that you're going to hear in the workshop. And please feel free to stop me at any time and ask questions. Okay, so I'm going to tell you how quantum gravity constrains physics at large scales. And when I say large scales, I mean cosmological scales. So a lot of the constraints are going to be statements about scalar potential or the vacuum energy. But usually when we think of quantum gravity, oh, by the way, also before anything, I should say, for some of you, this might be, very old, very, very familiar things, maybe except the last few slides. So I apologize for that, but for the rest of you, please feel free to ask questions about anything that doesn't make sense. Okay, so when we think about quantum gravity, sometimes we think about very, very UV scales. But then how does that have anything to do with largest length scales in the universe? How does that have anything to do with the IR scales? So let me do a quick review on some of the energy scales that appear in quantum gravity. And we have a big kind of theoretical experimental framework, which is string theory, to learn about these energy scales. And I'll go from low energy to high energy. So the lowest energy scale, so this is our mass ladder. We're going to go from low energy to high energy. Probably the lowest energy scale that we can think of is the energy scale associated with the Hubble, the observable universe. So the length scale for that would be the whole, length scale of the observable universe, the Hubble horizon. We can think of that as the curvature scale on, large length scales. And if you have a scalar potential, your scalar potential is a contribution to, the energy density. Therefore, generically, it sets a minimum for this energy scale. So in reduced Planck units, the Hubble scale is usually at least the square root of v. And this is the IR scale that we can have in a cosmology. But then in string theory, one of the things that we've learned is that it is generically we have a tower of weakly coupled states. So let me give two examples of this. So for example, if you have some internal compact dimension, so not the 3+1 large dimensions that we know of, but if you have some compact internal dimension, the bigger that dimension is, you get lighter tower of states. And the way to think of these is that these are just the higher dimensional particles that have momenta in the extra dimension. And these are known as the Kaluza-Klein particles. But then if you also have the string itself, the fundamental string, when you turn down the coupling of the string, because the same coupling also controls the coupling of the string to graviton, and therefore sets the mass scale of the string, then you get a tower of string excitations. Again, these can be very light. So this energy scale is above your Hubble scale, but there's still a lot of room from here to Planck scale. So we're going to see what else can be here. But before that, I should say, so this tower scale emerges when we have a tower of weakly coupled states. There is also a beautiful relation, which I won't explain, I won't talk about it much here, between this energy scale and black holes, which is that when you have a black hole and you make it small enough such that its temperature reaches this energy scale, then it becomes unstable. And one example of this instability is called Gregory-Laflamme instability. Another one is the Horus-Polchinski transition. So there's a very nice way that even black holes know about this energy scale. Okay. Then we go up. There's another energy scale that in the literature is known as the species scale. The way to think about it is that your gravitational effective field theory is not just the Einstein term. We think there's a series of higher derivative terms. And typically, even when we integrate something out, we get a series of higher derivative terms. But the point is that there's an energy scale that we cannot go above that effective field theory really breaks down, and there's no effective field theory description. To give two examples of when this happens, if you have large extra dimensions, then the higher dimensional Planck scale is a bound, so you cannot have any effective field theory description above that. Or if you have, again, weakly coupled fundamental string, your string scale is an example of that. You cannot go above that. Okay, so the reason this is called species scale is because you can make this lighter than in Planck, the more species of light particles that you have, because these will radiatively contribute to the renormalization of Planck scale. Okay. Then you have the Planck scale. So Planck scale, you should just think of it as the energy scale that is set by just the Einstein term in your effective action. So if you didn't know about higher derivative corrections, you would have naively thought that this is the quantum gravity cutoff. You would have naively thought that this is the energy scale at which everything becomes strongly coupled. But of course, as I just explained, when you do have these higher derivative terms, that can be a different energy scale. And then when you go even higher up this energy scale, there's a threshold above which you start having black holes. So in other words, black holes have some minimum mass. You cannot make a black hole arbitrarily small, because when the black hole is too small, the curvature of its horizon is too large. So there's no sensible way that you can think of its horizon, because horizon implies that we can trust Einstein gravity near the horizon of the black hole. But if the black hole is too small, that Einstein theory breaks down near the horizon of the black hole. Okay, so there's a rich hierarchy of different energy scales, and even this is really a simplified version. You can have multiple towers, and then these have analogs on the black hole scale. But there's a rich hierarchy here, and these energy scales can be different, but they're also related in a very deep way. So one of the easy ways that these are related is that because you want your Hubble scale, which is this IR scale, to be below where these towers become important and effective field theory breaks down. So this was an argument by Tom. You want to make sure that the potential is smaller than the mass scale of the tower squared. Or in other words, in units of reduced Planck, you want to make sure that square root of V is smaller than the tower scale. But then also you want to make sure that that's smaller than the species scale, and then the species scale is smaller than the Planck scale. Okay? But it's not that these are completely these scales don't know about each other, because when we want to widen these gaps, for example, if we want to make the tower scale compared to M Planck, or lambda species compared to M Planck, or potential compared to M Planck, when we want to make these things small, there is the same concept that makes all of these things small, which is you somehow go to some weakly coupled limits of your theory. And because there's the same reason that makes all of these things small, this is telling us that these energy scales need to be related to each other. It's not like, in other words, there's some really deep connection between how these energy scales depend on one another. And that's really the core reason that we expect scalar potential, which is something very IR, determines cosmology on large scales, to know about quantum gravity. It's not that quantum gravity is something UV that doesn't know about scalar potential. All of these things know about each other. This is a very kind of 30,000 feet view of everything. Okay, so far, I didn't tell you how these things depend on parameters of the theory. More specifically, these things in quantum gravity, in string theory, tend to depend on scalar fields that you have in the theory, the light scalar fields that you have in the theory. So let's be a little bit more quantitative to see how these things depend on scalar fields, because we're going to need that to connect it really in a quantitative way to cosmology. Any questions so far? Because all of these are kind of non-trivial concepts if you haven't heard of them, but okay.
You say again for lambda subtest.
Yes, thank you for the question.
And so I think I get dilutes of Planetower by dimension. H lambda subtest. Say that again.
Yeah, excellent question. Thank you. So let's say you have an effective field theory like this, and this is schematic. I mean, when I write R to the n, I don't necessarily mean Ricci scalar to the n. I mean something that's contraction of n Riemann tensors. So when you have something like this, if the curvature becomes of the order of this energy scale squared, if you have an expansion like this, the effective field theory breaks down. Now, whenever we have an expansion like this, it doesn't mean that scale is the quantum gravity cutoff, because sometimes you might get some expansion, not exactly like this, similar to this, because you've integrated something out. But in string theory, there is some energy scale that you cannot integrate things back in and get a good effective field theory. That's it. Like above that energy scale, this local description, effective field theory description, breaks down. So something that's actually in a very deep way related to this is to understand why this notion of locality just breaks down in quantum gravity is we cannot measure things at arbitrarily small distances. Like in non-gravitational physics, we can do experiment and we can make the impact parameter small enough and energy high enough, and then we can measure small distance physics. In gravity, if we make the impact parameter too small and energy too large, it collapses into a big black hole in the middle. So in some sense, as we tune up the energy, first we start probing smaller and smaller distance physics, but then again that distance goes up because you create a big black hole. So there's some minimum length scale that it even makes sense to talk about a local description, like effective field theory, and that scale is set by this.
Why is that not just the Planck scale, or is that Planck scale minus
questions
something
back here.
more of?
Sorry?
Can't hear the questions back.
Oh, so the question is that why is that not just the Planck scale? Yeah. So yeah, that's a great question. So in intuitive way, I mean, this was the original kind of proposal for that, and the reason it was called the species scale is that because graviton couples to everything, when you get more and more states, then these can run into loops and contribute to the propagator of graviton, and then it can make gravity strongly coupled at a lower energy scale. But again, we have examples of this that we understand top down. That what is this energy scale? For example, if you have a higher dimensional theory compactified in a circle, you already know in the higher dimensional theory you're gonna have terms like this suppressed by the higher dimensional M Planck. So that's going to give you an expansion like this that's not suppressed by the lower dimensional M Planck, but the higher dimensional M Planck, which is related to the lower dimensional M Planck, but can be much smaller than it when the size of the extra dimension is large. Yeah. Does that make sense? Yeah.
If you take the string theory example, I would say they're not above, but distance is smaller than the string scale, the string length. However, D branes probe smaller distance.
Yeah.
So how do you tell where are those?
Yeah. So D branes. You mean the horizon size of D branes?
Yes.
Yeah. So exactly for D branes, because they're so D branes is a brane example of what I've written here. So for particles, when something is light enough that its horizon, the would-be horizon, it's so small that I cannot trust the gravitational EFT near its horizon, I don't say that this is a black hole. I say that it's a particle. D brane is an example of this. For example, if I have a stack of D3 branes, if I have a small number of them, I should think of it as D3 brane, because that would-be horizon is too small to call it a black brane. But when I crank up the n, now the would-be horizon becomes big enough that I can actually think of it as a black brane, therefore the ADS-CFT duality. So the black brane description would be when that D brane has high enough tension that I can actually trust the metric near its would-be horizon. Does that? Yeah. Any other questions? By the way, great questions. Thank you. Okay. Okay. So far I didn't tell you how these things depend on scalar fields. All I told you is that there's some parameter space, and when you move in a direction that a sector of your theory becomes weakly coupled, these gaps widen, and because there's a common reason for all of these gaps widening, you should expect these things to be related to each other. Okay. Now let's try to make that, yes?
In this hierarchy, should I think of these things separated by an order of magnitude, or is that an order of magnitude? Okay. So good.
Yeah, good question. It really depends on where you are in the moduli space and the scalar field space. You can make them parametrically far from each other as you go to these weak coupling limits. But there is this finite region of your parameter space on the scalar field space that it's kind of a special region that things are strongly coupled, and these things can be of the same order. But when you typically move to weak coupling limits, then these gaps, all of these gaps widen. Yeah. Any other questions? Okay. Okay, now let's try to make this a little bit quantitative. So let's consider one example. Let's say we have a higher dimensional theory in capital D dimensions. We put it on some manifold, for example, it could be torus, and then we come to lower D dimensions. And when you have gravity, the volume of the space becomes a scalar field in the lower dimensional theory. And this is true only when you have gravity. When you don't have gravity, essentially that volume is part of the metric in the higher dimensional space. I'm emphasizing this this is going to be a recurring theme. A lot of the things that I say really are very specific to gravitational theories. And moreover, when you canonically normalize the scalar field, meaning that if you want to make sure that its kinetic term is 1/2 d mu phi squared, the way that that volume depends on scalar field is in an exponential way, and that coefficient depends on these dimensions. I will soon replace these with the d with 4 because the title of the program is our universe. But for now, let me stick with general dimensions. Okay, so and then moreover, what is the mass of these Kaluza-Klein particles? So these are just particles that have momenta in the internal dimensions, and those momenta are quantized because now your internal dimensions are compact. So the bigger you make the extra dimension, the lower those momenta can be, and the lower their perceived mass in the lower dimensional theory. So you get this exponential fall off. Okay. Again, this is only true. This promotes to a scalar field only in gravitational theories. Okay, what is another example? In string theory, when we have a fundamental string that has graviton as one of its states. Sorry, did I see a hand somewhere? Okay, so when you have a string that has graviton as one of its states, there is again a scalar field in your theory that controls the tension of the string. It's called dilaton. And if you have excitations of the string, then the mass of those excitations are related to the scalar field, again exponentially. And again, this is not true for every string in string theory. There are strings that they don't have this exponential dependence. However, the ones that are gravitational, the ones that have graviton as one of their states, they always do have this exponential behavior. So again, gravity seems to be something important in this pattern. And these two observations, were part of this thing called distance conjecture that Kamran and Hiroshi proposed. That whenever we take a scalar field to infinity, we always get a tower of states like this. So the weak coupling limits are much better understood, much more under control. And when you go to these weak coupling limits, a new structure emerges because there's a new weak coupling description that you might have not known that it exists, but it always exists. Okay, so now, based on many examples in string theory, there is a good amount of evidence to believe that these two examples that I showed you are kind of canonical examples that whenever you go to an infinite distance limit, whenever you take a scalar field, you take it to infinity, either decompactification happens or a fundamental string becomes tensionless. And if that's true, now I can use the numbers that I showed you in the previous two slides to find bounds. And there are 4 inequalities that are very helpful inequalities. These only hold in the asymptotic region of the scalar field space. But before that, I also need to explain to you what is this nabla here. Like, what do I mean by this? So note that we don't have just one scalar field. We can have multiple scalar fields. And so things can depend on multiple scalar fields. And this scalar field space has its own metric. That metric is set by the kinetic term in the action. So for example, if we have multiple scalar fields labeled by I, and have something like this. And this gives you a metric on the space parameterized by these scalar fields. And what this nabla is, this is telling you that what is the size of the gradient vector as you take derivatives with respect to these different directions when you compute it with respect to this metric. And you get these different bounds. So the first one is telling you that asymptotically, always there is a tower of states that goes to zero, very fast. The second one is telling you that the scalar potential goes to zero fast enough. The third one is telling you that that species scale is always exponential, and there's an upper bound and a lower bound for it. And then the final one is actually very interesting. I just wanted you to know that there's also this interesting relation, equality, that in the infinite distance limits, the inner product always seem to be fixed. Okay, I promise you that I will go to d equals 4. So here it is. But in the future slides, I might go back to d. but these numbers are good to remember. So these three inequalities are good to remember just so that you have some, like benchmark values. So the first one is telling you that when you go to weak coupling limits, you expect to have a tower of states that their mass goes to zero exponentially fast. How fast? That fall-off rate is bigger than 1/√2. The second one is telling you that the exponential potential goes to zero fast. How fast? The fall-off rate is at least √2. And the last one is telling you that your quantum gravity cutoff has both a lower bound and an upper bound. Okay, any questions?
So that distance, that nabla,
Mm-hmm.
I understand it's the units of Planck.
Yeah, oh, great question. So everything is done in reduced Planck units. Yeah, everything.
But it's basically the distance in the phi space.
Yes, so this is, so to be very precise, when I write, for example, this, what I mean by it is derivative of this m, which depends on your scalar fields with respect to, for example, phi I, and then also its derivative with respect to phi j, and then contraction of this with respect to this inverse of gij, and then square root of this. This is specifically. Okay, any other questions? Yeah.
Is there any problem with the potential, like the gradient of the potential being like order 1?
Yes, so great question. Please keep that. I mean, I will come back to that question, but really that eventually, if you want to connect it to our universe, that question will be addressed in one of the future talks in the program. But George,
potential being order 1 or gradient of the potential over potential, which one is the answer?
So I assume you're talking about this, right? Great. Yeah. Gradient of v over v. Yeah, being order 1. Yeah. Okay. So related to what Cameron is saying, it is so. Typically, it is raised as a puzzle that why is it that not only the value of, you want to call it cosmological constant or the vacuum energy or potential is small, but also why is it that it seems so flat? Why is it that the gradient of potential itself is very small? And so I will come back to this. It is very natural to expect the gradient of v and v to be of the same order. So if v is so small, the gradient of v is order 1 compared to v, but that would mean that gradient v naturally would be very small. But then you can ask specifically, is √2 going to get us in trouble? So for our late time cosmology, √2 seems to be too big. However, this is for asymptotic. These are the asymptotic inequalities. We might not be, in this asymptotic, we're probably not in the asymptotic region of the scalar field space. There are other inequalities that we think hold also for, every point of the scalar potential. And those are consistent with observation. But what is consistent with observation is not like 0.1, it's order 1. So, I mean, I'm spoiling something that George is going to talk about, but like the number is around like 0.8, 0.9. It's not, yeah. Sorry, George. Okay, any questions? Okay. Okay, so motivated by this, there have been, there's this program. It's called the Swampland program. It tries to understand, was started by Qumran, and it tries to understand what are the conditions, the consistency conditions of quantum gravity, things that in the effective field theory language, you wouldn't necessarily expect such conditions to hold. But when you add gravity, when you add quantum gravity, then you have these consistency conditions that your effective field theory needs to obey. And motivated by this, there are two conjectures that these are global conjectures. By global, I mean they don't hold just in the asymptotic region, but they're conjectured to hold everywhere in the scalar field space. So the statement, at least the statement of these conjectures is not, the statement is not that these only hold in the asymptotic region, but the statement is that they hold everywhere, okay? So the first one is called the refined de Sitter conjecture. And the statement is that there are positive numbers C1 and C2 such that, and these only depend on the space-time dimensions, they're order 1, and they're fixed numbers, constants, and they bound the way that your scalar potential behaves, meaning that at every point in the scalar field space, one of these two conditions is satisfied. Either your V is steep enough, meaning that grad V is bigger than some constant times V, or if it's too flat, then it must be that it's convex. So it must be that grad V is, sorry, not grad V. So this is the minimum eigenvalue of the Hessian. This is what this means. So it means that there's a direction that the second derivative of the potential is too negative. So for example, the implication of this is that if you have a scalar potential that has a critical point, that, you know, grad V is 0, the derivative of V in all directions is 0, this would be telling you that that could not be a local minimum. In one direction at least, it should be a local maximum. And this is why it's called a de Sitter conjecture, because it's telling you that you cannot have a stable, perturbatively stable de Sitter. It rules out de Sitter, but it's a conjecture, okay? Okay, but then you will notice that these constants here are not set. These are order 1 numbers. So there was another conjecture, Planck censorship conjecture, that, so the aim of this conjecture was if we have a condition like this, probably it should be connected to some physical process, some physical principle that doesn't allow V to become too flat. And when you have a scalar potential that's too flat, what happens is that you get, you know, very long periods of accelerated expansion. One physical process that naturally connects your IR scale in the theory, which is the Hubble scale, to your UV scale in the theory, and Planck, or it could also be lambda species, is this condition that what if cosmological expansions cannot be accelerated for too long? Here, sorry, this is wrong. This should say accelerated cosmological expansion cannot last long enough. No, cosmological expansion cannot last long enough. So the statement is that, so TCC postulates that you cannot have an accelerated cosmological expansion that stretches your Planckian perturbations, your Planckian fluctuations, all the way to Hubble scale. And I mean, mathematically, this is very simple. If you divide the ratios of the scale factor and multiply it by your, you know, if you move that here, let me actually write this over here. If I start with some mode that has length scale of 1 over m Planck, then if I track it with cosmological expansion, I want to make sure this is smaller than my horizon size. And if I move this HF here and m Planck here, there I get TCC. Okay. Oh, and also the TCC is short for this, Planck censorship conjecture. And like specifically, eternally accelerated expansion, I mean, whether it's power law or de Sitter, it violates TCC. So inflation is very much in tension with TCC. Okay, but you can say, why should I even believe something like this? You know, it's a conjecture. What is the motivation for it? Actually, before getting to that motivation, let me first tell you what it implies, and then I'll get to the motivations. So what does it imply if we believe TCC? The first thing is that bound that I told you about, the infinite distance limit, which is also called the strong de Sitter conjecture by Tom and collaborators, sorry, by Tom, that tells you that this grad V over V asymptotically must be big enough. That follows from TCC when you have an exponential potential. But then what can it tell us about not the infinity of moduli space, but like inside, you know, if my scalar fields are not taken to infinity? Specifically, if you have a potential that is monotonic from in this range phi I to phi f. So for example, let's say I have a scalar potential that just decreases from here to here, you can show that TCC would imply this inequality. It would tell you that at every point in this range, there's an upper bound for V. And that upper bound is given by an exponential function that has this fall-off rate of 2 over root d minus 1 times d minus 2. Now, this is a weaker bound than 2 over root d minus 2, so this allows the potential to be a little bit flatter. But it's a condition that is true for even the inside of your moduli space. And so one way to think of this is that if, for example, your scalar potential has some maximum in your scalar field space that is of order of Planck, and then it has this tent shape that is, inside is Planckian and then it starts decreasing. This is telling you that there's this almost average notion of grad V over V that is bounded by 2 over root d minus 1 times d minus 2. So phenomenologically, when we think of model building, this should be the natural bound that we're thinking of, not this one. And this comes out to around 0.8. So again, just a teaser. Yeah. Okay. But the implications that I told you so far is if you have a monotonic potential, you can also ask, what if I have an unstable critical point or I have metastable critical point? For those, it also bounds your scalar potential to make sure that your lifetime is sufficiently small, that the accelerated expansion doesn't last. And the bounds are very similar to the Sitter conjecture, at least for this one. Okay. Before also telling you what is the motivation for this, let me tell you what is not the motivation for this. So there's this common lore that if you have modes that start from Planckian and then they exit the Hubble scale, your QFT breaks down, your effective field theory breaks down. That is not correct. There is no quantum field theory breakdown here, right? Just a simple way of seeing that why that's not correct is that if you, for example, take the Sitter space that obviously has this feature, there is a coordinate for the Sitter space that is a global coordinate. And in global coordinate, you can take modes that are, for example, below some energy cutoff in the throat of this, bounce. And their energy everywhere in the Sitter space are going to be sub-Planckian. Because they're going to redshift both in the future and in the past. So this is a perfectly good mode expansion. And in fact, so in that work with Hayden and Paul, the main point of the work was something else. But something that we did was, essentially, we saw this story. We went back to flat slicing coordinate. And then we asked, so what is exactly happening and how we can generalize this to any accelerated expansion to show that there is always a good set of modes. And what happens is that because of the Hubble friction, if you start with something and then trace it back in time, it's not true that its average momentum is just going to go with the scale factor. There's something more complicated because of the Hubble friction. And we showed that there's always a tame set of modes in any accelerated expansion. So this is really not an effective field theory problem. There's something more. Yeah.
A complete set of modes.
So meaning that at every given point you can have energy scales that are smaller than the Planck scale. Yeah.
And I can write every function which
Yeah.
doesn't have curvature.
Yeah. So the point is that you can adjust your modes slightly, and you can have wave packets that are the same in the UV, but then you just change that wave packet in the IR a little bit, and then you resolve the trans-Planckian issue. Yeah, it's a little subtle. Yeah. Okay, so it's not a QFT problem.
This also sort of like is the same, for instance, when doing things in a Schwarzschild space time. People also talk about like.
Yes. Oh, excellent. Yes. So it is. So also okay. So there are similarities, there are differences. The similarity is that, yes, in Schwarzschild you also have, for example, for the infalling observer, you have good modes. That would be similar to how the infalling observer here in the global de Sitter has those modes. The differences, however, is that in TCC, it's the the free-falling observer that is seeing that mode going from curvature scale to Planck scale. And in black hole, that transplanking issue only happens for the hovering observer, not for the infalling observer. And that's really physically different. Okay. Any other question?
So I guess, what then is the is there any sort of VFT argument for the TCC if there's not a
No, not to my knowledge. There's no. I don't know of any EFT arguments for it. Yeah. So yeah, but the motivations are not EFT. Okay, so now what are the arguments? So I told you what is not an argument, but what are the arguments? I mean, the first one is that really probably the most convincing one. I mean, this depends on who you ask, but one of the most convincing ones is that it didn't, like these scalar potentials that we see in string theory, especially in the asymptotic limit, didn't have to satisfy this. That some like such a simple statement about the physical processes, and they happen to satisfy it. Every single case that we can calculate in all directions of scalar field space. I mean, there are examples that we're not sure, but it's because we don't know how the scalar potential depends on specific scalar fields. But in every single example that we can fully test it, it's unquestionable. It's good. The second motivation is that it is related to these other conjectures that we have. We also believe them. And this is just one example, but it is also related, for example, to weak gravity conjecture. There was this work that we had with Miguel and Irena and Kamran that in a non-trivial way is related. But let me just give you one example of how it's related to one of these other conjectures, specifically the emergent string conjecture. So if I take those bounds for the species scale and I say, I just consider this simple setup. This was an argument by Damien, Kamran, Max, and David. If I consider a very simple kind of setup where my species scale somewhere in the middle is Planckian, in the middle of moduli space, and then it exponentially falls off. And then I also remember that my square root of my scalar potential needs to be smaller than species scale to make sure Hubble is smaller than species scale. The lower bound on grad lambda species over lambda species gives you that interior bound, which is very interesting. It's very non-trivial. And then the asymptotically, because you want V to be smaller than m squared, you get that asymptotic bound. So because of the relation that V has with lambda species and m tower, then emergent string conjecture for those two things gives you the asymptotic and interior version of TCC. Yeah. Okay, well, you might say, okay, this is coincidence. So let me give you some other bottom-up arguments for it. So let me first start with the bottom-up argument for the asymptotic. However, let me just say, all of these arguments are going to assume something other than EFT because it's not going to be an effective field theory argument, and that assumption is motivated by quantum gravity. Okay. Okay. So in general, because the notion of space and metric is very fuzzy in quantum gravity, because metric itself quantum fluctuates, we've learned from many years ago that the sharpest way that we can define quantum gravity is by observables sitting on the boundary. For ADS space, this means that you have correlators on the boundary of ADS. For Minkowski space, it means that you have scattering amplitudes on the boundary of Minkowski. For de Sitter, there are proposals for it in this DS-CFT correspondence. Bless you. And really, the way that these observables are defined in Minkowski and ADS, it's the same formula. It's not a different formula. It's just that in one case, it's momentum space, and the other case is position space. Actually, you can define it even in momentum space in ADS, it becomes Mellon amplitudes. But let me just walk you through this formula. So here you have an endpoint function, but then you multiply it by the inverse of propagator, and then you take some sort of limit. If you're working in Minkowski space where momenta of the outgoing particles localize on some value, you take the momenta from off-shell to on-shell. If you take ADS space where the position of these particles on the boundary go to some position on the boundary, you take the limit of positions going from bulk to boundary. In the first case, this is LSC formula. This gives you scattering amplitude. In the second case, this is just the ADS-CFT correspondence. It gives you the CFT correlators. then you can apply the same thing for cosmological solutions and ask, under what circumstances I can have sensible boundary correlation functions. And there's a list of consistency conditions that I assume for these. So one of them is that we want to make sure that these are non-zero when points are not collinear. And then the second one is that we want to make sure that they're dependent on the initial state, meaning that even if it converges to something, you want to make sure that it doesn't wash out the initial information. And it turns out that if you have a power law accelerated expansion, this doesn't exist. Interestingly, in de Sitter it works if you have exponential accelerated expansion. The reason is because Hubble scale stays fixed. So mass over Hubble stays fixed, and in that case it works. But if you have power law accelerated expansion, and that's why you have the SCFD. But if you have power law accelerated expansion, because Hubble goes to zero, then essentially mass over Hubble becomes infinitely large, things infinitely localized, you cannot define correlation functions. Okay? So this is saying that you cannot have accelerated power law, eternal accelerated power law. And for exponential potentials, that's exactly the infinite distance inequality that I was showing you. So this assumption from holography that there should be boundary observables, that tells you TCC for infinite distance limits. Okay, but that's only about the fall-off rate of potential at infinity. How can I learn something about interior? So this is based on a different work with Qianshu Liu and Paul Steinhardt. Let's consider the following case. Let's say I have a potential like this that is first flat, and then it goes to something with exponential fall-off. So I have two stages of cosmology. In the first one, I have long accelerated expansion, and the second one, I have decelerated expansion that is satisfying TCC. So it doesn't run into the problem with the previous slide, but let's see if there's another problem that you run into. So because your equations are time reversal symmetric, you can consider a different solution. That's the CPT conjugate of this. That starts with a decelerating contraction, and it goes to accelerating contraction. So this is the CPT conjugate of this. And for this, we ask the following question. What happens if we start with the zero particle vacuum state, if I trace this? Okay. So what ends up happening is that at this transition, when you just solve the modes here, you do Bogoliubov transformation, you get particle production with Hubble energy. And then if this contraction phase lasts too long, exactly the TCC time, then your effective field theory here breaks down. I want to be clear, there's an assumption here that I started with the vacuum here. There is a state that doesn't have any effective field theory breakdown. It's the analog of Bunch-Davis state here. That one is perfectly fine. It doesn't have any effective field theory breakdown. But that state would have infinitely many particles here. Okay. And really the most non-trivial part of that work was that this breakdown of EFT doesn't really depend on the details of the transition. Because we found the asymptotic behavior of the particle creation using WKB approximation, and it gave us a very nice way of getting rid of the details of the transition. Okay. So what does that mean? It means that if you have such a situation that violates TCC, then your effective field theory breaks down for the state that is vacuum on the boundary. The analog of this for ADS-CFD would be if someone said that I only have semi-classical approximation in the gravity theory for non-vacuum states. It would be very strange. Okay. So again, you tell that to effective field theorists, they would say that okay, that's fine. But from quantum gravity perspective, it's extremely weird to say that only effective field theory works for non-vacuum states. Okay. So based on that assumption that we want the effective field theory to work for the vacuum on the boundary, we find that any classical trajectory that connects your interior to the asymptotic should also satisfy TCC. Now, I have not, none of these arguments rule out de Sitter. all of these arguments only work when your classical trajectory somehow goes, like gets on rolling and these exponential potentials. For those, I don't have any bottom-up argument now. But I mean, it's very interesting that you start with this very simple physical process. It's true in string theory, it's compatible with other Swampland conjectures, and you also have these holographic bottom-up arguments for them in many cases. So these are the motivations, but it's still a conjecture. Any questions? Yeah.
So when you describe this vacua with particles or no particles, you mean for a free falling observer? A free falling observer that cosmology?
Yes. But the thing is that because here you have two phases, what we mean, so there are two different sets of mode expansions. One of them are with respect to, because when you have this transition, the positive frequency at like high k positive frequencies before the one phase becomes some combination of positive and negative frequency in the other phase. So even for free falling observer, there are two sets of modes that you can define in each one of these phases. And yeah, so the statement is that for the observer that can actually go all the way to the boundary of space-time, if you want to take the zero particle state for that observer and ask the space-time to not break down, your space-time better satisfy TCC. Yeah.
How should I think of an observer that can go all the way to the boundary? What are the restrictions?
So, I mean, in this example, because that's sitting at eternal past, it's just an observer that just happened to, exist since eternal past. But yeah, I mean, any observer that's just not moving, will eventually find its way in the future. Yeah. Oh, and one other thing. Note that because here the asymptotic is null, there's only one. So you don't have multiple Hubble patches. The observer actually has access to the whole universe because everything is coming back into the Hubble horizon. You don't run into the problem of De Sitter that the observer cannot really see all of the space-time because the observer can't.
What I was confused by is I would think that if an observer can go to infinity, then the vacuum at infinity has particles because presumably the observer is part.
Oh, I see. Yeah. So I'm not answering that question.
If there is a contrast between the condition for the observer to go there and the nature of the mode expansion.
Yeah, so I'm not modeling the observer itself. Like I'm not modeling what the quantum collapse of some measurement would be. Yeah, that is for now. For now, like God is doing experiment for us. So, yeah.
You're saying that if you start past infinity with a non-Bunch-Davies vacuum state, then you wouldn't have this.
So if you start, for example, in this case, if you start with something that's Bunch-Davies, that in this TCC violating, that as the modes come out, they're in vacuum. Essentially, if you start with the zero particles state of phase 1, then there's no effective field theory breakdown. And phase 2, you just end up with like with a state with many particles. But that's okay. They're redshifted, they're IR, it's okay. So, which is why it's not really an effective field theory problem because there's a section of your Hilbert space that that's typically what people assume that the state is, but it is an assumption. It's really an extra assumption that in that sector, effective field theory doesn't break down. But the point is that if you have a space-time like this, then you're saying that my space-time only makes sense in the state that is not the vacuum on the boundary. Typically in quantum gravity, we have a background, and then we define things that we define the effective field theory to reproduce the observables that we get from perturbing around boundary vacuum. Here, that doesn't make sense. Any questions? Okay, so what are the lessons? So there are three very important lessons, phenomenological lessons, that what is natural from quantum gravity that wouldn't necessarily be natural outside of quantum gravity. One is that for V to be exponentially small, it's very natural because we have exponential potentials all the time. There is an asterisk here because here, I'm not solving cosmological constant problem. Here, I'm saying that V can be very small compared to m Planck to the D, but I'm not saying that Y it's small compared to like electroweak scale to the fourth. I mean, that's a different problem. So that I'm not addressing. What else is natural? If your v is exponentially small, grad v is also exponentially small because these two are usually proportional to one another. So these are not just like two different fine-tuning problems, they're related problems. Another thing that's natural is that when you have v that's exponentially small, meaning that some sector of your theory is becoming weakly coupled, it is very natural to expect to have a tower of states that are weakly coupled. And their mass is also very small. And this is going to be very important in the talk that you're going to hear soon. These are going to be related to dark matter. Okay, I'm going to spoil. Okay. Okay. Now that so any questions about these so far? Yeah.
So I think people have probably thought this a lot. What does this mean for inflation model building? Are you forced to consider like warm inflation or multi-field inflation?
Yeah. So I mean, if you believe TCC, which again, like from effective field theory perspective, I understand someone might not find it convincing. From quantum gravity perspective, I think it's extremely convincing. But if you believe TCC, then inflation is in trouble, because I mean the whole point of inflation is so that you have an accelerated phase that everything comes out from Bunch-Davis, and then all of these modes that exited the Hubble horizon then come back in the Hubble horizon, and you get cosmological particle production. But yeah, let me say it differently. If things cannot, like if TCC is violated, then it would mean that inflation didn't even have enough time to solve the initial condition problem. Because one of the selling points of inflation is that when that acceleration happens for too long, then my sensitivity to the initial condition problem reduces, because everything that I had will kind of be pushed out of the Hubble horizon. Yeah. I must say there are other problems with inflation other than this. If you're interested, I'm happy to talk about them. Specifically, these like new numerical simulation with nonlinear GR. That to have inflation going, you need a certain amount of homogeneity, and then it will make it much more homogeneous. But there's this lore that inflation solves the flatness and homogeneity problem and all of that, because when you do linear perturbation, you can see that that's the case. But even for that linear perturbation to make sense, you need to be in the first place sufficiently close to FRW to do something like that.
I think other groups done simulations have got the opposite.
There are multiple simulations. They have different assumptions. There are different initial conditions. There's a big initial condition dependence. Yeah, I'm happy to talk about this.
I just want to say that I think you're presenting a controversial view.
I'm presenting what?
A controversial viewpoint.
Okay. So for the It is true. Yeah, there is on this. There's debate on the numerical simulation part of it. There's debate. Yeah, but also that's not my work. I must say. Yeah. Okay. But is there any controversy about the arguments presented here, subject to the assumptions? That I can take. Okay. So now let me just also present something new that's not a review of past works. So there is this is also kind of a shameless advertisement for an upcoming work that's related to these constraints. I have 5 minutes, right? Yeah. Okay. So related to these constraints on the behavior of the scalar potential. Okay. So you'll again see in George's talk that when scalar potential is of the order of, in our universe, the tower scale to the fourth, that's a very interesting case that might have something, we think is very well suited to describe our universe. And there's a very easy way of getting such a scalar potential. Specifically, if you have a supersymmetric theory, you compactify it on on some manifold, and then you break supersymmetry such that you get Casimir energy, and that Casimir energy typically goes like this. Now, one way to get a Casimir energy is using Shirk-Schwarz compactification, which is to impose anti-periodic boundary condition on the circle. And for this compactification specifically, if we happen to be in a corner of landscape similar to this, something very interesting happens, which is you can relate the scalar potential that you get from this theory to the free energy of a different theory. Because this anti-periodic boundary condition on the spatial circle, you can think of, it's the same calculation, it's the same one-loop calculation you would do to calculate the potential of this theory versus the higher dimensional theory at the temperature that is set by the inverse temperature. So you get this correspondence between a thermodynamic theory and a zero temperature theory. On one side, you say, if I want to calculate microscopic free energy density, I make the time circle Euclidean and I impose anti-periodic boundary condition. On the other hand, you say, if I want to do Schur-Schwarz compactification, I make my spatial circle anti-periodic. And the scalar potential of one is related to the free energy of the other one divided by T. Now, this is very interesting because now you can ask all sorts of interesting questions. What do it's very simple and trivial in some sense, but then it allows you to ask all sorts of interesting questions that, what do thermodynamic constraints teach me about Schur-Schwarz potential? What do Swampland constraints on potential teach me about quantum gravity at non-zero temperatures? So you can go both ways. I'll give you just one example of something very nice that happens. Positivity of entropy on the thermodynamic side exactly converts to this bound. Now, what is this? This is telling you that in the radion direction of the circle, V is actually pretty flat. Well, if V is positive, So it's telling you that derivative of V is smaller than or equal to 2 over root d minus 1 times the minutes.
Alek?
Yeah.
Question. When you put, let's say, like a Minkowski theory at finite temperature, there is an instability, right?
Yeah.
How does that?
Yeah. So, but a big part of the paper is exactly, this is an upcoming paper, this has not been done yet, but it's under in what sense this is a good approximation, because the thing is that this is microscopic free energy density. So this is, for example, when we say, I consider like heterotic theory at some temperature, sure, I can calculate free energy density that way, but I cannot have that fluid for very, very large,
Putting it in a box.
Yes, we're putting it in a box. And it is in some sense, it's approximate. There are some, hierarchy of energy scales that need to happen. Okay. However, I just do want to say, so first of all, this bound is saturated if you just do classical compactification. If you have some V in higher dimensional theory, you just do normal dimensional reduction, it is saturated by this. So this is telling you that quantum corrections will always make the potential a little bit flatter. Importantly, this does not violate TCC because this is about a bound in one specific direction, but TCC is about all directions. And this inequality assumes that thermodynamic phase has some adiabaticity. So we did this calculation explicitly for example, one loop heterotic amplitude. And what you see is that above Hagedorn temperature, actually this is violated. So this is only true when you don't have tachyonic instability. So this is shameless advertisement, just about some other ways that you can study this correspondence. You can ask, what happens if on the thermodynamic side, I turn on chemical potential? On the Schur-Schwarz side, that maps to turning on Wilson lines. So you learn something about axion potentials. What happens, what can I say about the stability of my critical points? Spoiler alert, you can say that every Schur-Schwarz critical point is unstable. Then you can ask, okay, what about just anti-periodic boundary condition? I include some sort of twist here. In that case, you have other sorts of positivity constraints. So this is just some shameless advertisement. Okay, thank you.